Dakotah. Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the awesome stuff. And I am super happy to have Dakotah Tyler with us today. Hello, Dakotah.
Good morning. Good morning. Thanks for having me. Lovely to be here.
Well, thank you so much for agreeing to talk about your very lovely article. Morning. So it is May 14th as we record this. So morning, so you must be on the West Coast.
Definitely on the West Coast, and it's not even really the morning. It's 11 something. So.
Well, you know, Los Angeles 11.
Right.
Great. It's very cool. Very nice.
Yeah.
So how's summer in LA? Is it starting to hit, or are you starting to warm up, or are we still sort of in that springy mode?
Yeah, it's still in the spring where,
Yeah.
any given day you may get up to the point where you're like, okay, yeah, I definitely need t-shirt and shorts. But it's pretty overcast today, so it's a little bit chilly. I
Okay.
like it though. I like the spring out west.
Cool. Very nice. Very nice. And Dakotah, what's your position now?
So I'm a PhD candidate at UCLA in the physics and astronomy department. Thank
Yay.
you. Thank you very much. Hopefully finishing up in the next year. That's
Cool.
the current plan. So,
Well, let me be the first to congratulate you, Dr. Dakotah.
oh, thanks. It does, I do like the way that sounds.
I do too. It's got the double D thing going, right? Dr. Dakotah.
Yeah, the alliteration is nice.
Very cool. Very cool. And Dakotah, what do you like to do for research?
So I'm really interested in studying planets, exoplanets specifically, right? So not in our solar system, but the planets orbiting other stars,
Uh-huh.
and really how they evolve over time. I've always been interested in the idea of like, is there life? Is it possible? Is it something that could exist? And before we get there, we
Yeah.
really need to understand how planets are evolving and what types of systems do exist, what types of systems don't exist.
Cool.
And the way that I contribute to that is by studying the evolution of planets.
Very nice. Beautiful. 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 And that is going to bring us to this very awesome APJ article. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. WASP 69B's escaping envelope is confined to a tail extending to at least 7 RSP. And Dakotah, take us away.
All right, thank you. So first, I'd like to shout out to my collaborators here, Eric Pettigura, Antonia Aklapchich, and Trevor David for all of their hard work on this. And it's a pretty cool paper that we put together.
Yes.
So, obviously we're going to go through everything, but you can see here from the title, we are studying this gas giant, a hot Jupiter that has its atmosphere not only escaping, but sort of spread into this long, thin tail
Right.
that's trailing the planet, that's multiple times the actual length of the planet itself. So it's extending way, way out there.
Okay. Very cool. Okay.
And that is the sort of the catchy part, right? That's in the title. But like I said, what we're really trying to understand is how planets evolve. So if you scroll down a little bit, you talk
Sure.
about the background here.
Sure. Absolutely.
Over the past 30 years, we basically went from 0 known exoplanets to about 5,600. I think we just crossed over the 5,600 mark.
Okay.
And
Okay. Cool.
that's obviously a tiny fraction of all the planets that do exist, but it's enough to do some statistics to start to understand the population of planets, like the demographics of what kinds of planets do exist, what kinds of planets don't exist, which are more common. And one of the big takeaways was that for sun-like stars, almost all sun-like stars have a planet that is between the sizes of Earth and Neptune,
Okay.
but on an orbit that's closer than Mercury's.
Okay.
So super short orbit, larger than Earth, smaller than Neptune. And we actually don't have one of these planets in our solar system, right?
Right. Right. Yeah.
Uh,
Doesn't
and
exist.
and that's that's a little bit interesting because I think as astronomers, a lot of times it's safe to assume that you're average, that you're looking at something that's average,
Yeah.
right? That's when you're looking at large numbers of things, that makes the most sense. But we may not be so average after all.
Yes, our solar system looks weird.
Yeah. And so, but as we take a closer look at this population of planets that we do know of, these ultra common planets that are larger than our super Earths, smaller than Neptune, sub-Neptunes, they're actually split into two distinct categories. It's not like just one big jumble of planets in that range.
Okay.
It's actually either a super Earth or a sub-Neptune, and there's very, very few planets that are in between those sizes. It's listed here about 1.4 to 2.0 Earth radii. So that it's rare to find a planet of that size.
Okay.
And we want to try to come up with an understanding what physical mechanism is at play that is driving planets to be sort of funneled into two distinct categories with very few in between. Yeah, a bimodal distribution.
Cool.
There's another feature that stands out, and that's that it's called the hot Neptune desert, and that's that we find very few Neptune-sized planets that are super close, like on 5-day orbits or less. It's almost unheard of. We find a lot of super Earth planets around there, but no Neptunes, which would be more gaseous planets. So we want to understand what's going on here.
Indeed.
You wouldn't necessarily expect nature to be so discriminative in its planet producing ability, right? There must be something
Some driving processes, right?
Right? Exactly. And there have been multiple theories that are these mass loss theories that sort of start from a position that, hey, probably nature actually is just making a big jumble of planets that are of a certain size, but that for some reason these planets are losing mass, and they're either losing a lot, so much that they kind of become rocky. They lose so much of their atmosphere.
Okay. I'm with you.
Or if they're massive enough, sufficiently massive, they can hold on to their atmosphere, and they stay puffy. They stay gaseous.
Okay. Interesting.
So these mass loss theories, I mean, theories are great in science because you can come up for a theory to explain anything. But as an observer, which is an important job, you have to collect the observational evidence. Like, we need to see.
Absolutely.
You have to catch this. Now, one of the things about this mass loss, the erosion of the atmospheres of planets, it happens from high energy, the radiation that comes from the star.
Okay.
So you can just imagine a planet that has a bunch of gas. You heat up the gas. What happens to gas when you heat it? Ideal gas loss. Gas expands.
Right.
Expands enough, it can leave the planet. And the only thing that can sort of hold that atmosphere there is a sufficiently massive core.
Yeah. Okay.
And apparently, this process is so efficient that it's almost complete. A planet, when it's born, either has enough mass
or doesn't
to contain the atmosphere, or it doesn't.
Yeah.
And it happens so quick that when astronomers look billions of years later, millions of years later, these planets are already either in one category or another.
Yeah. Okay, that makes sense.
So there's a problem with catching that in real time. It can be difficult to catch it in real time because it happens so quickly.
Okay.
So what we did in this project, and what other groups have done as well, is tried to think of a nice experimental setup that nature has provided with us, where we could see this mass loss happening in real time.
Yes.
Which means that you either need to observe a really, really young system where it's still happening at a high rate and hasn't been totally completed yet.
Right.
Or what you could do is you could look at a planet that just had so much gas that no matter how much it loses,
yeah, okay,
always going to have more.
Right.
Like yeah, you can kind of like push the odds in your favor to be able to see it.
It's the
And
infinite gas tank.
exactly. It's a yes, it's a infinite gas glitch. So that's what we did with WASP 69B. If you scroll down a little bit, we can look at some of the properties of the system.
Let's look at this one. Okay.
Yeah, so it's orbiting a K star, so a little less massive than the sun, about 80% as massive as the sun,
Okay.
80% the radius, and a little bit cooler as well.
Mm-hmm.
And down there, you can see that the mass of the planet, it's about a quarter of Jupiter's mass. So
Yeah.
less massive than Jupiter,
Okay.
but a little bit larger than
Yeah.
Jupiter.
Yeah.
So, it's Jupiter, uh, it's much less dense than Jupiter, I guess is what I want to say.
Yeah. Right.
Of
Okay.
course, this is because it's on a ultra short orbit, like a 3.5 day orbit, or 3.8 days rather. So you got this big gas giant orbiting super, super close to its star, getting tons of radiation,
Right.
heating quite a bit and expanding. So, this system is sort of primed for us to be able to see it losing mass in real time.
Yeah.
Now, this we were not the first group to observe this planet. There have been other groups that observed it, and interestingly, they both noticed that it was leaking some material. Helium is what we're looking at. We're looking at this particular helium feature.
Okay.
It's called
Okay.
stable helium.
Uh-huh.
And one group saw that it had a slight tail that was about 2 times as long as the planet.
Okay.
Another group didn't actually detect any tail.
Okay.
And so there's a little bit of discrepancy there. And,
Right.
we were hoping to kind of add to the conversation and clean up exactly what's going on.
Cool. Okay.
Um, we scroll down a little bit. Here's in figure one. Actually, let's go down to figure two. I think figure two
Okay.
shows a little bit better what
Okay. Let's do figure two.
we're at.
Elapsed time, wavelength. Okay. I'm with you.
So these are our transit observations. We're doing transmission spectroscopy. So as the planet transits in front of the star, it blocks out some of the starlight. That's one of the ways we know the planet is there. But if you think about the edges of the planet, you've got some starlight that is gonna penetrate the atmosphere and go through the other side, come
Yeah.
and hit our detectors, and now we have sort of this fingerprint of the spectrum of the planet atmosphere.
Cool.
And you can see what we saw in this plot right here. That's why I really like it.
Okay.
So here, the darker color sort of represents a an absence of any change in helium as we look at the star. So at the
Okay.
bottom of the star, we have this negative time, which is just time before the transit occurs.
Got it. Okay.
So we've got a bunch of green down there in the bottom because everything is about the same. There's a little bit of fluctuation due to things in the star, due to instrument noise, but pretty much it's green. And then at around minus 1.5-ish hours, you start to see this brightening, which is actually a shadow. A little bit confusing, but
Okay.
what we're seeing is a dip
Okay.
in helium compared to what the helium looked like before the transit.
Yes.
So this is the planet itself actually crossing in front of the star, and the starlight that's going through the atmosphere is getting absorbed by this helium feature, this 10830 helium feature.
Okay. Okay.
So we're seeing some helium absorption.
Okay.
And then what you would expect is to see the absorption stop when the planet ends its transit, when it leaves the disk of the star.
Okay.
But what we can see here is that there's actually a continued absorption that goes all the way to the top of the plot. And I'll show a plot here in a second that illustrates this a little bit better. But one thing that we wanted to check for, you can see the panel at the very top. There are these vertical blue lines,
Yeah.
and these are telluric features. So this is like
Ah.
in Earth's atmosphere.
Uh,
A lot of times what happens is the Earth's atmosphere has water, and
yeah.
it gets it sort of like contaminates the spectrum that we're trying to look at. We actually lucked out. So you can see that there is a blue line to the right of the gray dashed double line right there. And that's our helium line, the gray line. The blue line is some water. We like lucked out. It's not, there's no contamination there. We would have just modeled it out if there was.
Oh, right. Okay.
Okay, so let's keep going. This is
Cool.
kind of like an overview of what we saw. We get into the analysis a little bit more.
Mhm.
Can you scroll down?
Yeah, let me absorb here for a sec.
Oh yeah. You have a
Do you remind me what the double dash line is here?
Oh, sorry. Yeah, that is the helium feature that we're looking at. So it's a triplet. So there are these two features that are really, really close to each other. And then there's this single line that's a little
A
bit,
little less right here.
yeah.
So here's
And this is the feature that we're looking for. This is going to be helium that is in the atmosphere of the planet.
Yeah. Okay. I'm with you. I'm good. Okay. Onwards. Down.
Yep.
I'm with you. There's our observations.
Yeah, so it was just over the course of a night. We try to get as much of that pre-transit baseline as we can, because that's where we're gonna compare the rest of the night to. You know, how is the helium that we're seeing changing relative to when we knew that the planet wasn't there?
Right.
Yeah.
Where were these taken? What observatory?
Keck
Keck. These are Keck. Cool. Okay. Nice.
with the near spec instrument on Keck.
Yeah. Yep. Oh, there we go. Near sec. Okay. Good. Okay. Downwards.
Yep.
Down. Let's go to figure 3, figure 4.
Okay. Yeah. So here in figure 3,
Yeah.
we are pretty much zoomed in on those gray dash lines that you were talking about.
Right.
And this is just that one helium feature that we're focused on.
Yep.
And if you get close to the screen, you can see that there's this pre-transit baseline that's in black. That is the if you look at the y-axis, it's the highest up, right? So there's the least amount of absorption of helium in the pre-transit baseline, which there shouldn't be much. But the blue line then is how much helium we see being absorbed in transit while the planet's in front of the star. And then that red line is the helium absorption post-transit when the planet is gone.
Okay.
So if there was no helium when the planet left, we would expect that red post-transit line to sort of match up 1-to-1 with the black pre-transit line.
Yes. Okay.
So, cool. All right, let's go down one.
Okay. So there's a difference between pre and post. Okay. And let's go 81.
Let's zoom in a little bit on the planetary rest frame.
Okay. And this is also the helium. Yeah, right. Helium.
Yep, same thing.
Yep.
So this is basically the same as figure 2, but just zoomed in on the helium that we're interested in.
Right.
So here we can see a little bit better because the contact points are noted on the plot. So T1 is when the transit starts.
Okay.
And right above it, you can see that there is some additional excess helium. T2 is when the planet is fully on the disk of the star. Okay. T3 is when it starts to leave the disk. And then T4 is when the planet is gone.
Okay.
So because this is in a planetary rest frame, what we would expect is that the helium, this brightening on the plot, should be hugging those two dashed white lines.
Yes.
But that's not what we see, right? What we see is that the absorption is actually being blue shifted.
Correct. Yes.
Away from the planet. Keep in mind, as the planetary rest frame, this is what the planet is basically seeing.
Right.
And not only is it being extremely blue shifted, but after T4, when the planet is completely off the disk of the star, continued absorption for over an hour. Gotcha. Right? So planet's gone, but we're still seeing something. There's still a bunch of helium there. Let's go down a little bit.
Interesting. Okay. Let's slide down. It's figure 4. And then we got, here's the equivalent width.
Yeah, we can. So this is another way to look at the same thing. So we can actually, I think we can go past the equivalent width.
Okay. Ooh, I like this one.
Yeah, let's go right here.
Oh, it is
So
nice.
the interpretation there
Yeah.
is that this extended helium absorption that we're detecting is a long tail of the helium that already escaped the planet,
Yes.
right? And this on the left, this is a 2 scale, simple schematic of what it looks like as the planet is leaving the disk of the star and has been gone for quite some time. We're still seeing a very strong detection of the helium, and it's not only present, it is blue shifted, meaning that it's coming towards us.
Yes.
Right? It's accelerating towards us. On the right side here, we can see a top down, like a bird's eye view of what's going on. And you've got this really long tail that is accelerating pretty fast, 23 kilometers per second
Yeah.
towards the observer.
Yeah. That's very blue shift. And what is the significance of the red dash line on the left? It's not.
Oh, so the red dash line is basically the last observation that we got, where the planet was, right? We know how fast the planet is moving. We know how long we observed it, so we can sort of like come up with this time and length that the is from. Yeah.
Very cool.
Yeah.
Very cool. Okay. I like
Okay.
it.
So, it's important, I guess, here to note that we didn't see the full extent of the tail. We got observations for up to 1.3 hours after the planet left the disk of the star, but we had to stop because the sun came up. Our sun came up, so we couldn't see the full extent of the tail. So it could be much longer.
At least 7 RP.
At least 7 RP for sure. All right, let's continue to go. So that early on we had a picture that this is what was going on. There was this extended tail.
Yes, yes. Okay.
And what that tail is, right, is it is mass from the planet. It is mass. It's mass. And what we really want to be able to do is estimate how much mass the planet is losing
to keep the tail. Otherwise, the tail will go away.
Right. That mass loss rate, and our understanding of these mass loss mechanisms, we should be able to adjust for the fact that this is a much more massive planet. And if our theory is accurate, then we should be able to within reason sort of predict what this planet, the mass loss of the planet is going through, and ultimately the fate of the planet in terms of its
right. To go back to our bimodal distribution. So we're looking for what's M dot. Okay.
Right. The mass loss rate. So we calculated this a couple ways. We tried to come up with an order of magnitude estimate. There's a lot of uncertainty there. If you think about what we're looking at, the planet is, obviously we don't see the planet, and the star itself is a point source. Right. So when we see all of this helium, we can come up with an estimate, just assuming that the helium is sort of evenly distributed across the star, which is a big assumption because that's probably not how it's distributed, but it's order of magnitude. And so if we just estimate a sort of a column density, we can try to figure out, with the amount of helium we detected and the amount of light being blocked, how much each individual helium atom is absorbing. We can convert this into an overall mass loss rate. So there's a lot of assumptions here in this order of magnitude estimate. And some of the other ones important to note are that we assume that the specific helium feature that we're detecting is is some like nominal fractional rate of the total helium that's in the atmosphere.
Okay.
Because we're only detecting helium in the metastable state, which is going to be
Yeah.
smaller fraction compared to the overall helium.
Cool. Yeah.
Then we assume that there's a primordial abundance of helium compared to hydrogen.
What I was born with. Yeah. Okay.
Right. So another assumption, but a pretty sound one.
Great reasons.
And then we can convert that tiny, the small amount of, I say small amount, it's really a small fraction of helium that we detect in this state.
Okay.
We can try to estimate an overall mass loss rate of helium and hydrogen.
Yes. Okay.
And the rate that we got with this method, if you could scroll down just a little bit, it's either at the bottom of this page or the top.
This here looks like.
Oh, estimated mass loss rate. Oh, this is for a different method.
Right. That's a 1D, but okay, comparison. Okay. Let's see. What are
Yeah,
we?
so you can actually see that they're about the same. I think it's the last sentence right here.
Oh, here it is. Here it is.
One Earth mass per billion years.
Yeah. Okay.
Yeah, about 10 to the 11 grams per second. So a lot of helium is being lost around this planet, and every billion years it loses the equivalent of the mass of Earth.
And we can go to table 1, but remind me what the mass of the planet was.
It's about 90 Earth masses.
Okay.
So 25% the mass of Jupiter, 90 times the mass of Earth. So, it's a lot. An Earth mass is a lot to an Earthling, but on the Watch 69b, it's really not that much.
So if we waited 90 gig years, it'd be all evaporated.
Yeah, right. But as a K-star, we know that, at most it's going to last 15, 16, 17 billion years.
Right.
So, this planet, according to these calculations, is going to be safe. It's going to be protected against ever being completely stripped, which is the, part of the reason we look for the hot Jupiters when we want to study this, because we know that, we're going to be able to see the mass loss, and they're sort of protected against being totally stripped.
Cool. Very
so good. That, this number is pretty much in alignment. It's in agreement with the other groups.
Yeah, the other one I mistakenly.
Oh, no. So this was another estimation for us where we assumed a symmetric Parker wind and the mass loss rate. It's a different way to estimate the loss rate.
Okay.
It's not but we saw this is not a symmetric configuration though. We saw there's a tail, so it's not a spherical.
But we're going to pretend it is.
Yeah, I think it's safe to do this for a comparison to other observations.
Yeah.
So I guess it's precise, but perhaps not accurate. Okay.
There you go.
So if we keep on going.
Okay, so we got our mass.
Get into the comparison with the previous observations.
Okay.
That's something that was a big surprise. This super long tail that we observed was not by other groups.
Right.
And now we want to be able to explain that. Why the inconsistency? Is there true variability? If we look on the planet, the figure to the right here, figure 9.
Figure 9, helium light curves.
You can see the light curve. Yeah, so this is I think we're used to seeing the white light curves for planets that transit, and this is a helium light curve. This is what the transit looks like in helium, and the sort of transparent observations there in the background were taken with Carmenes by a previous group, Nortman et al.
Okay.
The year before our observations. And the big difference that you can see is that the transit is a little bit more symmetrical. Like they do return to baseline slightly after T4.
Yeah, they're getting there.
blue and purple. So there's a little bit of extended absorption. But if you compare that to the black line,
Right.
which is what we saw, you can see that we actually don't recover the baseline until the very end.
Wow.
And even that is a data, there's some noise there in the data. So
Uh-huh.
we're clearly seeing absorption for longer than they did.
Okay.
And one of the big
Like noise.
points that I wanted to address here was, what are the potential sources of this variability?
Okay.
So one of the things to consider is that all three groups observed with different instruments. We
Okay.
use the Keck telescope, which is 10 meters. So that's big. And in astronomy, it's nice to have a large disk collecting the light. Carmenex is on a smaller instrument.
Okay.
So that could affect. They could just have not had quite as strong.
Yeah. Because it is definitely noisier.
It's definitely noisier, which is what you would expect, having a lower signal to noise.
Definitely, yeah.
So, it's possible that there's like a strength of signal thing going on there.
Okay.
However, there was another group. Their observations were a little bit different. They were just photometric observations.
Okay.
Grata 2020.
Okay.
And I don't actually have that on a plot showing that or anything.
That's fine.
But they don't have any velocity information. They just kind of have it's photometry, right? So they just have like a brightness, and they don't see any evidence for a tail in their observation.
Yeah, right.
So that could mean that it's just very short, or very thin, kind of like very diffuse, and they couldn't detect it. But at any rate, what we detect is conclusive. It's like there's no ambiguity. There's this extremely long tail that is the planet. So there's some other possibilities. If we scroll down a little bit,
Okay.
we can talk about some of the potential sources of variability.
Okay, T2 minus T3. Then we go to figure 11. Where would you like to go? 10,
Scroll
11?
down a little bit more.
Okay. All right. We got some scale heights going on there. Talk about.
Okay, here it is on the right. My bad. If you can scroll up just a little bit, we have these. Yeah. So the first, here we go, right here, about midway on the right column. The first is that, so here we're talking about the sources of variability.
Gotcha.
There's different signal to noise in each instrument. The instruments also have different resolution. We were able to rule out resolution-driven variability.
Okay.
But there could also be stellar variability.
Sure. Absolutely.
As we're working through these, I think something that kind of hops out to us is a huge unknown, is that there is going to be variability in any star that we can't account for. Like, we understand the sun pretty well. I mean, there's still some mysteries about the sun, but we've been observing it for as long as we've had solar telescopes.
Right.
And we have the Parker probe, which we send in to dip into the sun's atmosphere, so we can see how the outflow of particles from the sun is changing over time. But we don't have a good measure of this for other stars. There isn't a really good way to detect variability within the star. Right. And that's really important for a few reasons. So first of all, the helium feature that we're observing is actually excited by extreme ultraviolet radiation that comes from the star.
Yes.
So it's populated by XUV, extreme X-ray, or X-ray and extreme ultraviolet, but it's depopulated by a little less energetic UV. So like in the mid UV, will depopulate it. And obviously a star gives out both XUV and mid UV. I mean, the star is emitting across the spectrum. But it's not really well known how variability within those different parts of the spectrum show up in other stars. So I could easily imagine
Right.
looking at this, making those same observations that we made.
Yeah.
And for whatever reason,
Yes.
the star was putting out a higher amount of mid UV,
Yeah.
and the XUV was remaining constant. And
Yeah.
we just depopulated the state. So it's not like the tail isn't there. We just can't see it.
Yeah. Correct. Okay.
You know,
Okay.
so you can kind of think of the star behind whatever the star is doing as like a flashlight that, depending on its own ultraviolet and XUV output, is shining lights on different parts of the tail. So that's one thing that could be happening.
Okay. We'll come back.
Another thing that could be happening is, as the star goes through its own cycle, its own solar, like our sun, you know, right now we're having these.
Yeah. So, yeah.
Yeah, right now we're having our own like solar storms, these geomagnetic storms. Basically, what's happening is the sun is really magnetically active, and it happens every 11 years. Right now, there's a lot of sunspots. If you have your eclipse glasses, you can throw them on, and you can actually see the sunspots right now that are due to high magnetic activity on the surface of the sun.
Yes.
And you know, there's going to be variability that a star is going to naturally have from just being in that very natural periodic magnetic cycle.
Okay.
And we don't know where other stars are in their cycle.
Yeah.
We don't know how long the cycle is.
True.
You know,
okay, that's a problem.
that's not something that we have access to. And that also could lead to variability in the stellar wind.
Yes.
So, I mean, again, just to tie back to the northern lights that we're experiencing right now, you know, what's happening is the sun is blowing off always. It's going through its own mass loss process. It's literally emitting charged particles, protons and electrons. And those particles, they slam into our atmosphere, and they hit molecules in our atmosphere. And when they hit them, you get a flash, you know, that energy that's given off in a flash of light that's
They get excited.
purple, right?
Yep.
But when the sun is more active, you know, there's a higher chance that it's sort of blowing off larger clumps of these charged particles.
Okay.
So, you know, that's a solar wind. It's like a, you know, coronal mass ejection.
Right. Which implies a variable, a changing m-dot.
Exactly for the sun.
Right. So
The stellar wind is what's responsible for carving the tail, for sculpting the tail.
Okay.
So
yes.
we you know, we talked earlier about assuming a spherical outflow.
Yeah.
And if you just heat up a ball of gas, you know, energy conservation tells you that it's a sphere, it's going to emit in all directions evenly. Okay. But if you crank up the stellar wind, what happens is the stellar wind can kind of penetrate that natural outflow and suppress it a little bit, and force, like, the pressure from the star itself will force that outflow into a flattened tail that is behind the planet.
I'm with you.
And that's, you know, models show that that's how you get these tails. It's not necessarily a matter of how much material is leaving the planet. It's a matter of how much stellar wind, how strong the stellar wind is from the star.
Yes. Good. Cool. I'm with you.
Yep. And variability in the star surely is going to lead to differences in the stellar wind. It's going to lead to differences in the UV spectrum. Yes. And, you know, those aren't things that we have a great hold on. But what we do know for sure is that regardless of whatever variability is going on, we absolutely detected a tail, a really long tail that is extending 350,000 miles. It's being heated to 10,000 Kelvin. It's you know, it's a very, very extreme environment.
Very cool.
And even at 1 Earth mass per
Mhm.
year, per billion years,
Billion years, yeah, gig
mass
year.
per billion years, this planet is going to be safe against ever being totally stripped. But, if we just, for a nice thought experiment, imagine that instead of 90 Earth masses, this planet was 5 Earth masses or four.
Ooh, ooh.
How long is an Earth mass gonna really last on that planet? Well, not long at all. The rate would actually be
Oh,
higher because it's got less gravity, so it's not.
gravity, right?
So this is this adds to the mounting like smoking gun evidence of photoevaporative mass loss that's driven by high energy radiation
Yes,
from the star itself.
cool.
And an interesting sort of, and I don't know if this is a good time to plug in, but I think
Sure.
it works. Future work here
Okay,
with this.
let's save that. Actually,
Okay, okay,
I want to save that because I have
okay.
a
No,
question.
that's cool.
But very good, very good. Dakotah, I want to thank you so much for walking us through your very awesome article.
Mhm. Yeah, thanks.
Yeah.
It's fun, always fun to talk about. This is my favorite planet. My first author. This is always going to be the most special planet.
Oh, very good. Very good. That's awesome. And you definitely touched on it there at the end. I do want to push on that a little bit. Where do you think we go from here, given the published article? So is there additional data sets? Are there plans to do, let's say, maybe, data sets in a few years to see if what sort of maybe transients you're coming on to? Would other lines other than helium be of interest? Things along these lines. So just sort of next steps on where we go with this favorite planet of yours.
Absolutely. So I think a little bit bigger picture here. One thing that we can still continue to do is look for this mass loss in younger systems,
Mm-hmm.
which again, it's a little bit harder. Younger stars are noisier. There's more variability, a little bit more difficult. There aren't tons of young systems, right? Like most of the stars that we look at are older. That's the way that's how it works.
Yeah.
So, we continue to look for this in younger systems, but also, WASP-59b has sort of emerged as an interesting system because of the variability, right? When you make discoveries and you see things and they look different at different times, that's interesting.
Yeah.
And so there's there's some potential there for continuing to observe this planet and seeing if we can get a better handle on why this variability is occurring
Yeah.
by tracing it over, a longer amount of time where you have more than just a couple observations to look at.
Yeah. Fair enough.
And perhaps, uh, perhaps studying the variability in planets that are losing their atmospheres is one of the best or only even ways to get a handle on particular types of variability in stars.
Yes.
Like I said, there's only a certain number of physical explanations for the variability that we're seeing in WASP-69b.
Mhm.
And most of those are tied to the variability within the star itself. So if you get enough of those observations, you can kind of maybe piece together
Yeah,
what's happening in the star. Like, is the star going through its own cycle? And when you see the planet, depending on where the star is in its cycle, maybe you can say something to where the star is in its own magnetic cycle.
Right. That would be cool.
Yeah.
Very cool. Very nice. Very cool. Dakotah, thank you so much for walking us through your very lovely article. Very nice.
Yeah. Thanks for having me. It was a lot of fun.
Yeah, it was great. And that'll do, everyone. And I hope this makes your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.